In this video, we'll be going over Chapter 3.5, Complex Zeros, and the Fundamental Theorem of Algebra. So we have that the fundamental theorem of algebra is that if f of x is a polynomial of degree n, with n greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. And we also have we'll go ahead and I'll demonstrate this in an example, but we're going to go ahead and look at the complete factorization theorem. So if p of x is a polynomial of degree n greater than or equal to 1, then there exists complex numbers, possibly real, not necessarily distinct, a, c of 1, c of 2, all the way up to c of n, with a not equal to 0, such that p of x equals a times x minus c1 times x minus c2 all the way to x minus cn. Okay, so here's an example where we'll do that. So let p of x equal x cubed minus 3x squared plus x minus 3. So we go ahead and factor that. We factor by grouping, so we have that. Factored out an x squared and then a 1 from the second term, and I get x squared plus 1 and x minus 3. So I have that this 0 is x equals 3. The 0 on the left, we have x squared equals minus 1. When I take the square root, I get x equals, and then from our previous chapter on complex numbers, we know the square root of -1 is I. So we have x equals plus or minus I. So our zeros are 3, plus I, and minus I. So in this example, we have two complex roots. Alright, so our complete factorization using our roots is we use our complex numbers and our roots. But complex numbers are possibly real as well, because we have like I squared that equals -1. So we could do use that to get our real numbers. So when I factor, I use my zeros, so I have x minus 3, x minus I, and x plus are my factors. Okay, so if the factor x minus c appears k times in the complete factorization of p of x, we say that c is a zero of multiplicity k. So basically, if we had like x plus 2 squared equals 0, and our 0 is 2, we would say it has multiplicity 2 because it happened 2 times, basically. Alright, so our zero theorem is every polynomial of degree n is greater than or equal to 1 has exactly n zeros, provided that a 0 of multiplicity k is counted k times. Alright, so we're going to find the complete factorization of all 5 zeros of the polynomial. So we have 3x to the 5th plus 24x cubed plus 48x. Alright, so we have 3x we can factor out. So we have x to the 4th plus 8x squared plus 16. I could factor the x to the 4th plus 8x squared plus 16 using like our u substitution, where my u equals x squared. So if I had, or I could do like the perfect square trinomial theorem, where this is a perfect square, this is a perfect square. So my square root of x4 is x squared. Square root of 16 is 4. I just use that sign, and that's going to be squared. And so my factor of 3 of x is going to be 0, and then my factor of x squared plus 4 squared. So this factor is 0 for plus or minus 2i. So I could actually write 3 of x and split this into x plus or minus 2i using our factors, and that's all squared. And then I get 3 of x, and then I'm distributing the squared to both. So I get x plus 2i squared and x minus 2i squared. So 2i and negative 2i are of multiplicity 2, and they're double zeros, and then we have our 0 factor. So therefore, we have all 5 zeros because we have every polynomial of degree n. So this is degree 5. So we have n zeros, provided that there's a 0 multiplicity k. So we have x equals 0 is a 0. Then we have 2i, and then like 2i again because of the multiplicity, then negative 2i, negative 2i. So therefore we have all 5 zeros. Okay, so now we have the conjugate zeros theorem. So we've kind of seen this appear already, but if the polynomial p has real coefficients, and if the complex number z is a 0 of p, then its complex conjugate, z bar, is also of 0 of p. So here we're going to find, in this example, a 4th degree polynomial function f of x with real coefficients that has negative 2, 2, I as zeros, such that f of 3 equals negative 150. So since I is a 0, we know that the conjugate, negative I, must also be of 0. And we know from one of our previous theorems that it can be written in this form with our complex numbers here. So I'm going to use my roots in there. So I have x minus negative 2 is x plus 2, x minus 2, x plus I, and x minus I. And so I combine those, and this is like our breakdown of a difference of 2 squares, and that's x squared minus 4. The same thing for this is like a difference of 2 squares. So I have x squared plus 1 because I have, when I multiply these out, I get x squared minus ix plus ix minus I squared. And so I get x squared, these cancel. Then I squared is negative 1. So I get x squared plus 1. So this one's not a difference of 2 squares, but when I multiply it out, that's what I get. So then I could use my given information. So f of 3 equals negative 150. So I set it equal. I have negative 150 equals an, and I plug in my 3. I have 5 times 10, so I get negative 150 equals 50 an. So my an is negative 3. So I could, if I wanted to, I could plug that in to the original thing and then multiply everything out to get negative 3x fourth plus 9x squared plus 12. And then also just a reminder that the complex conjugate of 3 plus I would be 3 minus I. Okay, and then we also have our linear and quadratic factors theorem. So we have that every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. So basically, that's just saying, like, when you factor them, we know we finish factoring them if they're basically irreducible. So we have p of x equals x fourth plus 2x squared minus 8. So we're going to factor it into factors that are not irreducible. So we have x of fourth plus 2x squared minus 8. So that is going to be x squared minus 2 times x squared plus 4. And that's because we could do our u substitution again, where we have our u equals x squared. And then that would be like x squared plus 2. Let me use a u instead of a x. So if I have negative 8 and 2, I get 4 times 2. But then I do 4 minus 2. because 4 times negative 2 is negative 8, and 4 minus 2 is 2. So essentially, I would have u plus 4 and u minus 2. But then I know my u is the x squared, so that's how I get that. And then I could break those up even more. So I have x squared minus 2. And I could break that up because if I set x squared minus 2 equal to 0, I know that x squared equals 2. Take the square root, so x equals square root plus or minus square root 2. So that's why I could do these into 2 factors by using my previous theorem when you split it up. And then x squared plus 4 is irreducible, so we're not able to reduce that. But if I wanted to, I could factor it completely with complex coefficients. So that's how I could factor x squared plus 4, because if I did x squared plus 4 equals 0, I get x squared equals negative 4. I take the square root, and I get x equals plus or minus 2i. And then I could break it up into factors. So even if it's irreducible, we could still break it up into complex coefficients. Okay, that's all I have for this video.